now begin with the penultimate session of this graceful conference. In this conference, this is titled as Critical Metals for Emerging Technologies, Separation, Recycling and Advanced Application. In this session, we'll explore cutting-edge researches on separation, recycling and advanced application of critical metals.
We welcome our chair, Dr. Sumanta Bhattacharya. Professor Sumanta Bhattacharya, professor in the department, was an emeritus professor, former head of the department at IISM Dhanbad, and a Commonwealth Fellow with over 28 years of experience in teaching, research and consultancy. He has been honoured with the National Mineral Award, Coal Beneficiation Award and Aarti Mineral Beneficiation Award. He serves on editorial and advisory boards of international journals and has collaborated with leading institutions worldwide and has led numerous research and consultancy projects.
Joining him as the co-chair, we have Professor Sahendra Singh. Professor Sahendra Singh is a professor of Ore Geology and Institute Chair Professor at the Department of Applied Geology, IISM Dhanbad. His research focuses on ore geology, mineral exploration and nanogeoscience, with emphasis on gold and critical minerals. He serves as an expert member of Executive Committee of National Mineral Exploration Trust, Ministry of Mines.
I would now like Professor Shatrughan Soren to felicitate him with a bouquet of flowers.
एक और
This is a very difficult task. Everybody must be pretty hungry. And since morning everybody has been listening to a series of very interesting lectures. And problem of holding this session immediately after lunch is also not very bright, because then people feel little bit sleepy and all those things. And because of time constraint, always there is a pressure on session chairs to reduce the allotted time, which is not fair to the speakers. In this session, we have 3 papers, right? 4 papers. Okay. And time allotted to each presentation is 15 minutes. And the list of presentees begins with a very, very senior person, Dr. T. Srinivas. So I request Dr. Srinivas, please come on and please make the presentation. Dr. Srinivas is the current DAE Homi Setna Chair in BARC. After his retirement as an outstanding scientist and former head of the Mineral Processing Division in June 2023. His expertise is in mineral processing and hydrometallurgy. He has 120 research publications and received the Homi Bhabha Science and Technology Award in the year 2018 and the National Geoscience Award in the year 2014. He serves on expert committees on critical minerals. And in fact, those who are familiar with critical minerals, rare earth elements, they must be pretty familiar with the work of Dr. T. Srinivas. allotted is 15 minutes. Of course, he cannot exceed 15 minutes. I will be ruthless. But my request will be if he can reduce it by 1 or 2 minutes.
Yeah, definitely. Anjan has spoken, there is nothing remaining to talk. Anyway, good afternoon to all. So, first thing is my salutations to two eminent faculty members of Indian School of Mines. I think without mentioning those names, my presence here will not be justified. Professor T.C. Rao and Dr. Vishnu. I was having a lot of interaction with, they are actually father figures for mineral processing in the country. So we need to salute them first before my presentation on these, or my perception on these critical minerals. Okay, and then of course senior faculty members like Bhattacharya, Nikam Suresh, Suresh Mandre, all those people I know very well. So anyway, thanks to the present organizers of these critical minerals quiz. Now let me talk on what are the research needs for recovery of critical mineral values from mine and process waste. Because if you see any supply chain strategy, there will be three modes of execution. One is short, medium and long term. If you look into that perspective, especially if you see the definition of critical minerals, we find it supply versus economical usage of those things. So supply is one of the critical factors based on which this critical mineral definition has come. So if you want to go for any greenfield project or new projects, I think some equilibration. Any new mine, if you want to start, it will take minimum 15 years. These are the statistics from USGS. So if that is the time consumed in United States of America, 15 years, and you can think about India, what will be the situation. So in such case, we have to resort to the secondary and tertiary. People are talking about recycling and all, even in countries like Europe and Korea and all, it has not yet picked up that high. It is still 10-15% only. Lot of problems are associated with recycling option. Then the obvious choice will be secondary resources. What I mean by secondary resources? Essentially the tailings, mine dumps, slags, so on and so on. So my presentation will be focused on this particular thing, and I can tell you one thing. In fact, lot of work was done by very illustrious people earlier generations. Due to some policy disconnects, the extractive metallurgy got discouraged. Therefore, whatever that mental literature is there on extractive metallurgy, mineral processing, mineral beneficiation, all those things got disconnected. Otherwise, if you take any rare subject, you will not find the paper without the citation of Dr. C.K. Gupta and T.K. Metallurgy. That is the book which is cited at the most. You take the hardest of the hard, challenging extractive metallurgy, metal, the critical metal, beryl. It was carried out by Dr. C.V. Sundaram. So this is the time we have to go back to our yesteryears and see what our great people have done. They have done for different reasons. Only thing is, as someone was pointing out in the today, the phrase has changed it to critical minerals. Way back in 1950s and 60s, they were called prescribed substances. It used to be 14 or 16. Now it got enlarged to 30. And the definition of critical minerals is a dynamic one. One day we don't know, entire periodic table may become critical. Because US has got 50 elements as critical elements or minerals or whatever you call. Okay? So there is no sanctity of this, how many are there, 30 are there, 20 are there, 10 are there. It only depends upon the ingenuity of the scientists, how they are making use of that particular element for some niche publication. This is what is important. Now if you go, this is again, already on this, already countries like Australia, European Union, Canada and USA have realized and they found what can they do with this waste generated in their backyards. So once very important observation has come, you can see here it has come in the Science Journal very recently. What they are telling is US has sufficient geological endowments in active metal mines, and even if they recover 1% of them, 1% of them, they will be not so critically dependent on foreign countries for their supplies. And if they are able to recover 90%, then they are the leaders. How they are able to come up to this conclusion? It is not just like that. They have done extensive research, and under the critical minerals mapping initiative, they have analyzed 76 existing mines and 26,700 samples. Then only they found out. They have gone from macro level to meso level and nano level. That means up to PPB level, and found out where these things are available. So this is a very, very important observation. We should take inspiration from that. India also is doing mining for quite a long time. We never look back. We need to look back into our own mine dumps and all those things. Now if you see, even in our country, we have started National Geoscience Data Repository in 2016. But unfortunately, a third of it has to be looked for green deposits also. That is that among the obvious geological potential area, which is 6.88 lakh square kilometers, 2 lakhs is yet to be explored. So that is the position of India. So forget about what is there in the waste. So we need to do extensive exploration. That is the point behind today morning someone making a mention of we need to have lot of investment into this exploration. It is not just mere exploration. It should be coupled with a very, very highly sophisticated characterization. Without characterization, this exploration has nothing to, it will not achieve the desired end result. Now let's see. Again, these are some of the heat maps what different organizations have conducted or generated, that is base metal maps and PGE deposits, and our own Department of Atomic Energy has put a complete map of several places where these rare metal and rare earth occurrences are there. They have got that. We have been doing on this for quite a long time because most of these rare metal and rare earths are nuclear materials. That is the reason behind. Now coming back to, see, this is what I am telling. Characterization, multi-scale, multi-model and multi-dimensional. We need to go for remote sensing, for tracking where the deposits are there at 100 kilometer scale. Then comes your meso, micro and nano. That is, it ranges from hundreds of kilometers to PPB level. First you find out where the occurrences are there. Now we have got hyperspectral imaging, so many such things are there. IIT Bombay is doing, our own NGRA has got a lot of expertise in that. Many government departments are relying on the geophysical expertise of NGRA. Only thing is, sectorial expertise should be done. It is not the general expertise, but sectorial expertise. For that particular purpose, we should align our ideas. That is what is important now. So, if you look at, please bear with me. You can see here the scale, meso scale. We see the surface hardness, bulk density, resistivity, conductivity, and all those things. We have got a variety of measuring tools for those things. When you go to the meso, micro, and nano, we need to have this ICP and different variants of ICP. That what is it called? Micro XRF, and then of course what I'll say. What is that one? ICP-MS and LABS, those things which can go up to ppm and ppb level. Why? We will know in the following slides. And of course, all these things are required because all these critical mineral resources are lean in tenor and complex in mineralogy. So if you want to really find out that particular critical mineral or metal or whatever you say, you need to have all these things. Otherwise you will not be successful in that. So they are present in few labs. Now at least the government should encourage that such facilities should be there in a good number of laboratories, and people should have access to that. It should not be a monopoly of a single lab. That is what is fundamental change we need to have. Everyone claims I can do, but they will not allow. I should not name the laboratories. They will not allow others to come and use those things. That is that goes against the country's overall requirements. Now if you see, again today morning there was a mention, lean tenor, fine grain, disseminated. These are some of the characteristics of these critical minerals. And why I am mentioning these characteristics is, very startling information has come from European Union country, that is Netherlands. What they were telling is, because of adopting very aggressive processing conditions, especially in hydrometallurgy and all, What has happened is there is water scarcity, there is soil erosion, there is biodiversity loss and climate change. Already people are telling. See, on one side we are telling there is critical minerals are meant for clean energy transition. But if you look at the process, the roadmap for achieving that ultimate product, it is spoiling the entire environment. Already China has discovered the near Bayana Obo, 11 square kilometers of the area has got polluted with so much of chemicals. That is why European Union is scared of adopting any of these primary processing. Then KU level laboratory has shifted to solvometallurgy. That is a fundamental reason. So, and then if you go into the numbers, that is very important. It drives the point very nicely. An area of about 1 million square kilometers of our planet is now overlaid with mining related waste from all types of mines. This is about 0.67% of the total global land. Remember, already the waste generated is 0.67% of the total global land. Second thing is the greenhouse gas emissions. This is 10% of the total global energy related greenhouse gas emissions. This is a lot for one sector, the so-called mining sector, especially since it contributes only 6.7% to the global GDP. So this much of culprit it is happening. This mining and metallurgical extraction is creating to the environment. And why I am telling all these things is, this only shows the importance of the domain expertise of what is it called midstream, that is processing. Mineral beneficiation has got lot of importance in today's context. Without mineral processing or mineral beneficiation, I will say you will not be able to get yourself transferred to a high green metrics in that processing road. So let me go into the further. The key drivers in design of the resource recovery strategy is you should optimize your energy, you should have minimum water usage, and your surface footprint should be, green metric should be very high. Now let me, because of paucity of time, let me go to the next slide. I will go directly to the mineral beneficiation. Here we should have, our research should be focused on sorting of fine grained minerals, not coarse grained minerals. If we are not successful with fine grain, at least look into the major gangue and develop the sorting methods which can remove the unwanted things from the waste of whatever it is. Second thing is comminution and classification. This may not be necessary for tailings which are already powdered, but if you take slags, we have to have some method of crushing and grinding them. In such case, we have to go for those things, intensive grinding techniques. Then comes most important, that's separation methods. Gravity, magnetic and surface chemistry based separation methods. These three things, many of you, or at least people like Bhattacharya and all these things were there from quite a good number of years and all. What is great new in this? The thing is, all these things confined to laboratory only. If you take in India, no plant or pilot plant even is having something like the multi-gravity separator or Nelson concentrator or Falcon or anything like that. We don't have anywhere. We are stopping all our research at the laboratory level. It is not translational in nature. That is why we are failing everywhere. We should have, everywhere you see, two terms commonly used, scale and another one is on table. If you see, listen to the news, they will say the scale. We are lacking in that scale. We are not, scaling up of the process which we have developed. And lot of challenges come up when you take a laboratory process to a pilot plant to a full scale plant. Many challenges come and research is required at each and every stage. This I am telling with my own personal experience on uranium. So because of time constraint I am not elaborating it, but otherwise I could have taken a case study and explained you very clearly on one of the most challenging uranium mine in the country, for which BRC has developed in-house complete end-to-end solution. And that is one of the biggest uranium plant in the country as of date and adopting a very novel processing strategy. Right. So when it comes to magnetic, similarly gravity separation I have mentioned, magnetic separation also we have got high intensity magnetic separators. No one is using it except in clay industry they are using. Otherwise it is not used elsewhere. All those things we need to use. And then high gradient magnetic separator including superconducting magnetic separators. That is required because you require high field strength. If you don't have high field strength, some of these critical minerals cannot be captured from the waste selectively. Then of course surface chemistry based. We are talking about molecular recognition technology, development of designer molecules and all those things. How many people are using it in industry? Which industry has used them? We have got lot of expertise in chemistry. Our Ramanujan was telling, lot of laboratories are there. NCL Pune is there, BRC is there. So many places are there who are having synthetic organic chemistry expertise. And they can create any molecule. See, very recently we got for constrained molecules, buckyball fullerenes and all Nobel Prizes. That was done in University of Hyderabad long back by Professor Govardhan Mehta and team. They are pioneers in this. And highest number of publications in Journal of American Chemical Society are from Indian scientists on these constrained molecules only. So we need to leverage that expertise in chemistry for designing of these molecules. So unless we have that, we use that and apply them, we are stopping at some stage. We need to translate into application. That's what I am telling. Sectorial expertise is important. That is why mineral, so-called this critical minerals domain, it is a multidisciplinary in nature. Starting from a geologist, mining engineer, all have to work seamlessly. If they work in their own silos, we will not be able to deliver anything. That is why if you see in US, civil engineering people are working on minerals. That is the thing. Okay, next I will conclude. Okay, so I am just mentioning about NML and CSR laboratories. Very recently, they have looked into recovery of tungsten, which is 10 microns. Why I am mentioning about the particle size is, this is the challenge there. Fine particle recovery is the challenge. So they have used all these things, and why I am mentioning this is, they have carried out at a pilot plant scale, and they were successful in getting 100 times enrichment, from which is present at 0.02% in waste tungsten, which is used extensively in defense industry. Very blindly we are importing from China. I am part of that expert committee, that's why I am telling. But we did lot of work during 1980s and 90s. Many laboratories like IBM, BARC, AMD, and then CSR labs, they worked extensively on it. But in between they stopped everything because it was available freely from China. We did not continue that, at least that, what I will say, academic exercise or research exercise or whatever it is. So it stopped there. So today again we are looking, we want tungsten. How we are reinventing the wheel? That is a problem. So they were able to get 2.8%. There is 100 times enrichment. It is a very challenging problem. They addressed, they got it, and now they are setting up a pilot plant. Now if you see, BARC also has developed a superconducting high gradient magnetic separator way back in 90s and 2000 using niobium titanium white, which can give a magnetic field of 3.5 Tesla. It is only a field. And if you have the stainless steel wool of certain diameter, it will give high magnetic flux. So that will go very effectively in picking up particles which are even feebly paramagnetic up to the size of 5 microns. You can see 55 to 16% of the particles which are feebly paramagnetic in nature can be captured. That is the efficiency of it. We also blame ourselves. That time we did not take the, is it over? Superconducting, we did not scale up actually. We need to do that. BHEL was very much involved in this particular thing. There was a national mission on superconducting magnets and magnetic separators. Unfortunately, we did not go further in that. That's a bad luck. Now if you go to the next slide, this is very important. Why? Because other equipment we have to purchase from Australia, XYZ. But flotation, we know we can still rely on our own indigenous expertise. But the thing is, we have to design different types of reagents which are biodegradable or bioderived. The conventional reagents are not selective, especially if the things are present in very fine sizes and their concentrations are very low. So we need to have selective reagents and chelating type of reagents like hydroxamic acids, fatty acids, different derivatives of fatty acids, and these sulfides we are using xanthates so far. Xanthates will spoil the environment. That should be replaced by nitrile based reagent. Similarly, bioderived surfactants should be synthesized and used. Let me give one more extension to my hydroxamic acid this thing. China is achieving success in critical minerals because they developed more than 20 or 25 variants of hydroxylic acid functional groups, and they are quite successful in utilizing those things. So we need to do certain work on this, and we have to replace the conventional reagents with these things. Now anyway, let me go to the next slide. Yeah, this thing our Ramanuja has talked about. After in the value chain, first you do beneficiation, that should be followed by what is it called hydro or solvometallurgy, and we have got 12 principles of circular hydrometallurgy. It is nothing but comprehensive utilization of the mined material, reagent recycling, recovery of acid, and then optimum utilization of the energy, water, and so on and so forth. This we have heard enough from our Ramanuja. Let us go to the next one. Okay. Let us go to the specifics. Leaching, if you take, we have got some 6 types of leaching methodologies. One is in situ leaching, dump leaching, heap leaching, vat leaching, these things. There, very important observation is, in all these things, we need to use bio-based leachers. And here also, we should not give whatever reagent we want. These critical minerals are known to be refractory. If you take these bio-leachants, which we are using conventionally, they may not be able to dissolve this. Let us take from the nature some good lesson. University of California has done that. What they have seen is how the plants are able to break the refractory apatite and consume phosphorus. From that they develop some variants which will be able to break monazite. See, monazite is very refractory. Its melting temperature is very high and the bond strengths are very high. That is why rare earths require something like either sulfation roasting or temperatures above 800-700 degrees centigrade for breaking those bonds. But they have observed the nature. If plants can break the refractory minerals like apatite to take the phosphorus out of it, why not we synthesize a biomolecule which will be able to break monazite? And they were successful in that. Though the recoveries were 35 to 40%, but still they could do it. They had to optimize the process. In India also we did it. And we have got a green strong organic acid called methane sulfuric acid. We have to replace the conventional mineral acids with this type of organic acids. Yeah. When you come to the stirred reactors, that is what is it called reactor leaching, we have to replace the mineral acids very strongly. We should try to use ionic liquids, deputatic solvents and organic acids. They need to get the required attention. And then replacement of all the chemical oxidants with gaseous oxidants. See, oxidants like oxygen, ozone, hydrogen peroxide, these things will do the same job like other chemical oxidants. So we need to replace them with these type of things. Now when you go to, see, we in our own lab, we have conducted some studies on coal fly ash and how to recover the rare earths from that using the deputatic solvents.
Please.
Yeah, I will come to it. So quite success was obtained here. Okay, let me jump. Okay, so this is the recoveries and all we got, and we are going to set up a pilot plant in Neyveli Lignite Corporation based on these technologies. Now let me come to the last one, autoclave leaching. Let me just mention this. Why? Because here process intensification is very important. We have got several alternatives because again and again I am telling these critical minerals are very refractory. Therefore, we have to have very aggressive processing conditions. What are the techniques? Pressure leaching, microwave, sonochemical, plasma, mechanochemical and supercritical fluid extraction. But all the things down, they are not translated into industry. But if you take pressure and microwave, they have got graduated little bit. Now in this, what India needs to do? The thing is, we don't have, with personal experience I am telling, we have to have strong R&D for appropriate design of alloys which can withstand wear and tear at high temperatures and abrasive materials, because these are all multi-phase systems. These are not like pharmacy. Ours is a multi-phase system. So it gets spoiled within no time, autoclave reactors. We are using in our uranium plant. Say every 3 years we have to change. We don't have technology for magnetic seals. Whenever you are using pressure vessels, you have to have magnetic seals. We don't have technology. Okay? We don't have any expertise in making alloys at industrial scale. We do it in laboratory. But how to make it at industrial scale? We imported Hastelloy for our research purpose for the uranium project. But when it came to implementing in the pilot plant scale, we are now doing lot of research in BRC to develop the Hest alloy alloys. Otherwise, only US has got that Hest alloy 2000, which can withstand the corrosive environment in many of these hydrometallurgical operations. Inconel, this also we are importing. So we need to have scaled up versions of many of these advanced alloys. Now coming to microwave reactors, here there is a skin effect.
Dr. Srinivas,
Yeah.
my brother.
I am concluding. So anyway, just one line everywhere. The challenge in selective separation of these hydrometallurgical leach liquors is they are very lenient. You cannot apply solvent extraction straight away. Solvent extraction is meant for only enriched solutions. So you have to have adsorptive separation methods. So what we need to have adsorptive? You have to plug in selective things or functionalized bases. So we require functionalized ion exchange resins, functionalized solid resins and so on and so forth. Okay, you can see here modifications include the bottom line is it should be stereo specific and stereo selective. Then only you will get the selective. Second thing is we have to have nanofiltration. People are telling we can use membrane, but it will not work, I am telling you. Because the total dissolved solutes in any critical mineral solutions is more than 100 GPM. None of the membranes will work, I am telling you. None of the membranes will work. We have to design something which can withstand the fouling. Otherwise, in laboratory they will show 1 or 2 cycles, subsequently nothing. So, then okay, green solvents, all of you know. I will only talk about amide, nitriles, esters, ethers, alcohol, carboxylic acid. Those things have to be made as a functional groups and design the other part of it. Next, we have to use precipitation, not with the chemicals. We should go for organic acids and gaseous reductants. Hydrogen and all we should be able to use hydrogen peroxide as a reductant. Then the environment will be clean. With this, there are certain specific cases also, but ultimately I will say my summary is we have to go for resource mapping, advanced characterization tools for deeper understanding of deportment information, aggressive physical beneficiation techniques with emphasis on fine particle recovery, development of process intensification techniques and methods for resource dissolution, robust separation purification methods for mineral recovery, recyclability of that separation basis should be more, it should be recycled more and more number of times, capacity building for manufacturing of process equipment and commercial production of mining and specialty chemicals. We are importing from cyanamide. If you talk CSIR labs, very liberally they are getting from cyanamide. But same thing is not affordable for DAE. We cannot get 1 gram of hydroxylic acid from Cytec. They will not supply. The moment they see BARC, they will say no. So we have to have our own production and we did that. That's what. So we have to have that mining and specialty chemicals expertise. Your startup should be there for that. And then enhancing the scale of experiments. Most important. Improving the green metrics of the process scheme. Thanks you.
Thank you very much. Our next speaker is Dr. Ranjan Kumar Singh, who had been waiting impatiently.
We both traveled impatiently from Hyderabad.
Dr. Ranjan Kumar Singh is a scientist G in the Advanced Magnetics Group at DMRL Hyderabad with over 20 years of R&D expertise in magnetic materials. He holds degrees from IIT Roorkee and IIT BHU. His major achievement was establishing India's first samarium cobalt rare earth permanent magnet production plant. He has 2 granted Indian patents and received the DMRL Scientist of the Year award in the year 2013 and the Rare Earth Association of India Scientist of the Year award in the year 2024. Dr. Singh, please. Same time, request for time.
Yeah, thank you. Thank you for the introduction. Am I audible? Thank you. At the outset, I would like to thank the organizers for this wonderful conference, and especially DK Singh sir for having me here. So my topic for today's talk is thermal performance enhancement in samarium cobalt and NdFeB rare earth type permanent magnet. So if you look at the history of rare earth permanent magnets, these magnets were discovered in 1970s. The first magnet was samarium cobalt, and because it had 65% of cobalt, there was continuous research to replace cobalt with iron. Iron will provide extra magnetization, increase the magnetic power of the magnet as well as reduce the cost. So therefore, after 1970s, most of the research was concentrated on increasing the energy product of samarium rare earth permanent magnet, and subsequently SM2CO17 magnet was developed that contained around 15% of iron, reducing the total cobalt content from 65 to 58%. And 1980s NdFeB magnets were discovered that contained around 75% iron and no cobalt. So this was the R&D mode in which magnets were developed, where the major concentration was on developing this high strength powerful magnets. But if you remember, recently we had Sindhu, and before that we had Galwan incidents. So after Galwan incidents, there was our industry, it faced a problem for sourcing NdFeB magnets from China, and therefore there was initiative from NITI Aayog to develop this high temperature NdFeB magnet in the country, the technology for it, and this task was given to IRL, BRC and DMR, where IRL was to develop the rare earth oxides, and BRC was given the task to convert rare earth oxide into pure metals, and this metal was given to DMR for converting into NdFeB magnets. And this was done, and therefore I will be talking little bit about that work which was carried out on NdFeB magnet to enhance the operating temperature of magnet from say 100 degrees to 200 degrees. So I am from Advanced Magnetic Group. This group basically works on samarium cobalt and NdFeB magnets. Samarium cobalt magnets are mainly used for strategic applications like missiles, radars, submarines, aircrafts and drones. And also they are used in space, satellites. Most of the satellites, they have rare earth magnets for latch valve and actuator application and atomic energy. NdFeB magnet, on the other hand, is mainly used for commercial applications like electric vehicle, wind turbine, computers and metal. So therefore, if you look at the use of rare earth element, most of the rare earth elements, basically 24% is used for making magnets, either NdFeB or samarium cobalt. If you consider all permanent magnets, 58% is basically NdFeB magnet. And if you see, samarium cobalt is only around 1 weight percent. The volume, if you see the volume or weight, the worldwide production, it is only 1 weight percent. The reason being the samarium cobalt are used only for strategic applications. If we look at the rare earth elements, totally we are having around 17 elements. We can classify them into two, heavy rare and light rare earth elements. For magnet making, light rare earth elements like samarium, Nd and Pr, they are required because they couple ferromagnetically with iron or transition elements. Whereas when we want to improve the performance of this rare earth permanent magnet, we have to look for heavy rare earth elements like Gd, terbium, dysprosium, erbium. They couple antiferromagnetically with iron and increases the intrinsic coercivity of rare earth permanent magnet, thereby increasing the operating temperature of the magnet. So for defense application, if you see right now, we are having samarium cobalt and NdFeB type of magnets. Samarium cobalt magnets can further be classified into SmCO5 and Sm2CO17 type of magnet, whereas NdFeB magnets are basically either high energy or high temperature. For defense application, we are more interested in high energy type. And samarium cobalt, SmCO5, all the technologies were developed using SmCO5, the first generation technology. Now the latest technologies, we are working with Sm2O17 magnets, and that too, it has two types, high energy and high temperature. Right now we are in high energy, we are using high energy Sm2O17, but in future technologies we want high temperature so that the magnets can deliver flux at elevated temperatures. So why we require this kind of high temperature magnets? If you see in certain applications like submarine, missiles and aircraft, there is a constraint of weight as well as space, and in satellites there is a constraint of power also. So to overcome this constraint, we go for high energy for rare earth permanent magnet that leads to device miniaturization. So the device size can be reduced if you use a very powerful magnet. But when we are trying to reduce the device size, it will generate lot of heat also. So that is why when we are trying to reduce to after certain size, the temperature increases, and therefore we want materials where it can withstand the high temperature and still deliver the flux. We cannot add any cooling arrangement, especially in case of aircraft, missiles and submarines, because of the space constraint. So therefore we need the material itself to sustain high temperatures. So now the total research which is going on in rare earth permanent magnets is to develop high temperature rare earth permanent magnet that can deliver magnetic flux as well as sustain high temperature. Going back. So what do you mean by energy? I am talking about magnetic flux, magnetic energy. Just to revision of your class 12, if you see that this is the demagnetization curve in the second quadrant, and when I say high energy, it means that if you draw a rectangle below the BH curve, that the rectangle where BH max is written, the area of that rectangle, if you calculate and we find out the rectangle which is having the maximum area, so that is basically called BH max or energy product of a rare earth permanent magnet. And higher the value, the better the rare earth permanent magnet in terms of magnetic flux output as well as resistance to demagnetization. So basically it gives a combination of Br and Sc. Apart from that, from this curve we can derive other properties of permanent magnet also. But what do you mean by operating temperature of a permanent magnet? If you see, operating temperature is not the Curie temperature of a permanent magnet. If you see NdFeB magnet, it has a Curie temperature of 310 to 340 degrees centigrade, but its operating temperature ranges from 80 to 200. Similarly, 217, it may have a Curie temperature up to 850, but its operating temperature is limited up to 550 only. Why there is a gap between the Curie temperature and operating temperature? The reason is because when we use this magnet, there are different types of losses. One loss is a reversible flux loss, that the magnet is in operation, the flux of the magnet comes down, and then when the operation is over, the flux is again retained. So this is called reversible flux loss. It is generally happening below the operating temperature of the magnet. But when we go for above operating temperature, there is irreversible loss of flux. That means the magnet will start demagnetization in the operation. It will lose the magnetic property, and this is the cyclic demagnetization process. If you see that when we increase the temperature, the green line, which is the initial room temperature curve, the green line will shift towards this becomes the red line. Like here, it will come to here. I don't have a pointer right now. So ISC becomes here, and because of that, we develop a kink in the BH loop, and due to that kink, the magnet starts demagnetization over a cycle of magnetization and demagnetization. So therefore, cyclic demagnetization process leads to demagnetization during the operation itself, and that limits our operating temperature of the magnet. Coming to permanent loss, that happens when we heat the magnet above Curie temperature. So to increase the operating temperature of magnet, we need to increase the coercivity of a given permanent magnet such that when we increase the temperature, the fall in coercivity is less, and therefore we can have a magnetic flux output even at elevated temperature. Then we need to increase the coefficient of coercivity with respect to temperature, like beta value. How fast this coercivity is falling. First, the coercivity should be high. At the same time, the fall of coercivity with respect to temperature should not be very high. It should be gradual and slow. And then high Curie temperature. Okay, so this is the research facility which we are having in DMRL. This is a very unique research facility only DMRL is having. We are the only lab which can do research in rare earth permanent magnets, produce permanent magnets, and we also supply to our defense applications. So basically, rare earth permanent magnet process is a powder metallurgy process where we start from alloy melting, then go for powder preparation. The powder preparation can be through jet mill or through a ball mill process. Then we go for orientation of these powder in a magnetic field and do then compaction either through a magnetic field press or cold isostatic field press to get a green compact. In the green compact, we have particles which is having one particular orientation that decides the north and south pole of a magnet, and then we do centering and we do characterization to get the magnets. So coming to NDFeB magnets. NDFeB magnet, if you look at the microstructure, it has three major phases. This is the matrix phase, is the Nd214B phase, whereas at the grain boundary we have Nd-rich phase, and then we have some boride phases also. And apart from that, because rare earths are highly reactive in nature, we will have oxides, sometimes we have iron phase also. So many phases are there. If you get the whole process, technology is developed such that we can minimize these impurities in NDFeB magnet to increase the energy product. So Nd-rich phases, it plays a very important role for determining the coercivity in NDFeB magnet, because what it does is it encompasses the grains, and one grain and other grain, they cannot interact. That is during that magnetic coupling, it will break the magnetic coupling, and because of that you get very high coercivity. So that is the requirement to get the high coercivity in NDFeB magnet. So you can see that there are several elements in the periodic table which can be used to go directly to the grain boundary, such as gallium, copper and aluminium, and these are basically low melting point elements, and these elements, when it reaches the grain boundary, it further lowers the melting point of the Nd-rich phase, and because of this low melting point, it can easily encompass the grain and separate each grain from other grain. So this is what happens. This forms eutectic phase. When we add gallium, it forms eutectic phase as the grain boundary, and when this eutectic phase is formed, this is the decoupled magnetic domain microstructure. We can see that each grain is having its own domain, and one domain is not influenced by the other domain. When this kind of microstructure we get, then only we can increase the coercivity of the magnet. You can see by adding aluminium and gallium from 11.63, we are able to increase the coercivity by 230 kilowatt.
Dr. Ranjan.
So finally we will add dy also, because I told dy couples anti-ferromagnetically, and that gives the major push to the coercivity, and from 13 kiloohms we directly jump to 30 kiloohms. That happens because dy goes in the matrix of NDFeB instead of grain. First the grain is decoupled, then we put dy in the matrix, in the grain itself, and that increases the coercivity drastically to 30. And with this we were able to develop 200 gate NDFeB magnet that is widely used in electric vehicle. So the problem here is, like, this is an India-centric problem, because we are using dy to increase the operating temperature of NDFeB magnet, but the dy in India we don't have the resources for dy. It is very, if it is available, it is not yet explored fully. So therefore, at DMRL we had initiated a research program where we want to develop NDFeB magnets with similar properties without using much of heavy rare content. So that is the other way how to remove HRE content in NDFeB. So one way is to reduce the particle size of the grains, or to reduce the grain size, and when we reduce the grain size, it is reported in the literature that the coercivity of the magnet increases. But when we reduce the grain size of NDFeB magnet, there is a challenge that because of its highly reactive nature, this powder, it immediately oxidizes, or sometimes it can catch fire also. So therefore, to process this magnet with very fine particle size, we need special setups which is totally pressing, orientation and all magnet making process. It has to be done under inert atmosphere, and this kind of setup we have already established at DMRL, and with this we are able to produce 42 grade NDFeB magnets. And this has dy content of less than 1 weight%. Coming to 217 magnets, this magnet has very complex metallurgical microstructure, and this microstructure is developed after 5 days of heat treatment, where we see that it forms a cellular microstructure where the cells are basically 217 and the cell boundaries are 1,5 phase. And there is a redistribution of iron and copper in 217. If you see, 217 contains iron, copper and zirconium, where copper and zirconium is added to increase the corrosivity and Rn to increase the PR. But when we do microstructure and we study this microstructure, we realize that iron is basically concentrated inside the grain, whereas the copper is concentrated at the cell boundaries. And when we achieve this kind of microstructure, then only we get an optimal combination of corrosivity and this BR, and that is how we get 30 energy product magnet. But these magnets are only operational up to 300 degrees centigrade. And if you want to increase this operating temperature, this kind of microstructure should be stable up to, say, if you want to go up to 500, this kind of microstructure should be stable up to 500 degrees centigrade. The problem comes is when we go above 400, there is a diffusion reaction starts taking place where the Rn starts going towards the cell boundary and copper starts coming inside the grain. That destroys the total magnetic property of 217 magnets. So therefore, to overcome this problem, we need to identify composition where this property, the magnetic property is an invariant of iron and copper compositions. So we did a DOE experiment concept and we found out some region where iron and copper does not influence the magnetic properties of 217 magnets. And this is, if you see copper at 9.85%, the BR line is flat, and at the same time nearly corrosivity line is flat. So that means if you take above 500 and if there is a redistribution of copper or iron inside the microstructure, still the magnetic properties are retained, and that is how we developed 550 grade 217 magnets with a linear demagnetization curve at DM.
Kindly conclude, please.
So this is my last slide. So to summarize, these are the different, I have plotted energy product, room temperature energy product as a function of operating temperature. So the circle ones are the magnets which we have already developed at DMR, and ideally we see that when we try to increase the operating temperature of a magnet, the energy product of the magnet decreases. Say NDFE magnets have around 50 energy product, but when we try to increase its operating temperature to 200, its energy product decreases. Similarly, it happens for 270 also. So this is a major challenge. Lot of young minds, talented minds are there. If you can push this curve vertically, I am going back horizontally. If you can push this vertically, we will have the best magnets in the world, where we have optimum combination of energy product as well as operating temperature. With this, I will conclude the talk.
Thank you, Dr. Singh. Will be done by Dr. Ritesh Ruhela, Scientific Officers, Park, Mumbai. So he will be doing presentation on advances in selective separations of critical metals, a necessity for emerging green technologies. Dr. Ritesh Ruhela is a scientist at BARC, having joined in 2005 and holding a PhD in chemical science from HBNI. He was awarded the prestigious Marie Curie International Incoming Fellowship for postdoctoral research in the UK. His core expertise is designing ionic liquids and ligands for selective metal extraction, rare earth separations, radioactive waste management, and e-waste recycling. He has over 50 international journal publications and hold 2 international patents. Please.
So to start with, I first thank the CRISP organizers for inviting me to this critical metal seminar. I will start with some advances which we have recently done, and why they are required and why we have done these advances. I will come. So this your 14 rares, and then we have scandium, yttrium. So these are having the applications in different fields, and because we are having so many applications, these rare metals, you have to separate them to get some purity levels which will find applications. So this is a typical that flow sheet kind of thing, that why we should separate REs. REs produce a source as a mixture, and that the user they require RE at purity levels from 99 to 59 purities, and this is the usual the flow sheet kind of thing. you do mining, physical beneficiation, chemical treatment, separations involving precipitation, solvent extraction, then some solid liquid extraction and ion exchange. You can see that separations, we can reach till double line purity. And if you really go to 5-9 kind of thing, you have to have, that some kind of technique to have better separation factors, which is not till now achieved. And I will be dwelling into those things. So this is a typical liquid solvent extraction phenomenon. So we have some aqueous phase, then we are putting some organic phase. Organic phase is having that kind of that metal capturing site, and when you mix those phases, after contacting and resettling, the metal hydrated metal ion, that in aqueous phase your metal will be in a hydrated form, and the hydrated metal ion will be going into the organic phase. So the driving force of the designing of ligand will be how you can push the hydrated sphere with your ligand. So that is the whole designing thing, and we have to really think it in a way that okay, this kind of ligand can actually push the hydration sphere, can it solvate the metal ion, and then only we can get the metal ion in the organic phase. These are the commercial things which are available, Sinex 272, PC888, FR. These are used at commercial scales, but they have limitations till now, which has not been solved. So, this one. So, this is what we have till now for rare earth extractions. This is option 1. Conventionally, chloride medium, we are using PC888, P507 thing, widely well understood. Again, we have a nitrate and DBB mix. It is being used in US most of the time. And then, in all these two things, we need better solvent with high separation factors. And intensive research is actually going on in I think 4 or 5 groups around the world, where they are targeting high separation factors to bring the number of stages to lower numbers. Yeah. This is the thing which is recently coming up. So this is kind of a new class of solvents which we are working. These are task-specific ionic liquids. The task-specific means, or in UK we call it functionalized ionic liquid. So the thing is that you have an ionic liquid and you are putting some functionalities which is very task-specific. And they have, so the ionic liquids can be used as such as a diluent, and or we are putting a ligating functionality, and that can be used as extractant. The advantage is that they are non-flammable because they are ionic and they have a very low volatility, so they comes into the picture of green solvents. During my postdoctoral work, actually I developed this male process, and if you can see the separation factors, these are the 1,000 to 10,000 which we have reported. It is patented, and now a pilot plant is actually operating in Belfast, UK, 10 ton per annum, and it is now going to commercial scale around 400 ton per annum. In US, actually, there are a lot of group, Oak Ridge National Laboratory in particular, they are working on double ligand extraction system. So what they are doing, we have an organic phase, and the organic ligand we have that is used for the transferring of metal from the aqueous phase to the organic phase. And in fact, we have a second ligand that is actually water soluble, and that again we are having a synergy that the target metal should not bind with the organic soluble ligand, aqueous soluble ligand, but that it should go into the organic phase, and the interfering or the other metals, they should club with the ligand in the aqueous phase. By that procedure, they are also getting quite good separation factors. Apart from solvent extraction things, because many times we are dealing with that lean solutions. So lean solutions we are having concentration in sub-ppm range. So this non-solvent extraction options, this is called MRT kind of things that have come up, and the basis, the general basis is like that. You have a ligand and that ligand is designed on the basis of MRT. And these highly selective ligands you chemically graft it on a solid support, and on this basis actually two plants are actually running, two PGM plants and two copper refineries. They are actually operating at Boken, and I think this is IBC technology, but the capex is actually waiting. So I will just give another slide like this. HPLC also they are doing it in Norway, and they have actually sold 10 kg of 6,9 purity yttrium oxide. That is again a ligand kind of thing. So I will come directly to our approach. This is molecular recognition technology which we have developed in BRC. The basis of this technology is like that. You want to develop a metal selective ligand, and you have to do a little bit of theoretical calculations where the ligand, the design ligand, you can elongate the chains by putting some carbon linkers. Then it can be used for liquid extraction, and if the same ligand we can graft it on a solid polymer solid base, it can become as a solid polymer based resin. So the crux of the matter is how do you design a ligand. So actually if you see in the nature also that we have a very good selectivity in nature as well. So sulfur things, they are having soft metal will go to them like that. So on those hard acid based principles, we have designed the ligand depending upon their nature of donor atoms, the polarizability, and finally the conformational rigidity of the overall ligand. And for metal ion, we have ionic radius, hydrogen sphere, and in fact the nature and geometry of the complex. So we have to really optimize the things whenever we want to design a ligand. The thing is that if you go to empirical approaches, maybe you have to design hundreds of ligands, and that is not possible. So what we have done, we have we have made a kind of screening through DFT. So what helps in us that we can save time, we can save manpower, and of course chemicals, because we are not synthesizing those things. Then after screening of the ligand, we do some the thermodynamic calculations to actually see that most feasible mode of interaction between the metal ion and the ligand, is it possible or not. And because that after the theoretical thing, at the end of the day you have to apply it at the practical skills. So we do some calculations in solvent phase, like in dodecane and maybe some other solvent. So it will give you the confidence. Okay, then when we develop a ligand, it will go for practical application. So these are the genesis of our rational design, and the test of rational design is like that. So when we do some DFT, when we do design of the ligand, and those design ligands, we that parallelly we do some FTIR and then UV with NMR, and we do some experimental things. And when there is a close match between experimentally derived FTIR, let us say, and theoretically derived FTIR, when there is a close match, we know that okay, we are hitting that target, and after getting the close match, we start with the synthesis thing. So this is a typical thing. How do we proceed? So first we design the ligand using DFT calculations, thermomol, Gaussian, ADF. These are the different programs. Then we do synthesis at 100 gram batch, and later the process optimization at 1 to 2 kg batch. And parallelly we do the batch evaluation things, small columns and then scale up columns, and they are disseminated in scientific communication, and most of the time are technology transfers. So I will give you one or two examples, very recent examples by how we have done it. So this is a typical problem coming from IRE. So they want to separate yttrium from HREs in one of their stream. So actually the current state is like that. We have given, earlier it was given that thiocyanate based SX process, and it has provided quite a good separation factors for HRE over yttrium. The problem is that we are adding thiocyanate to give selective recovery. But again, the management of hazardous thiocyanate is a big problem. So getting a license for that is a little bit tricky. And again, because you have to manage thiocyanates, it is becoming a costly process. Okay, if you see the literature, there are some carboxylic acid based solvent extraction molecules which are available, like Na, then Ca100 and C12. They are giving workable separation factors, ease of implementation, but not available commercially. In fact, very few countries are having these kind of molecules. And in fact, if you see the structures, the carbon to the polar atom ratio is not that much, and because of that, they have a appreciable aqueous solubilities. So this problem when it comes to us now, so we don't think that okay we should develop these molecules. We straight away go think that okay we will develop some better solvents. So with that we develop this solvent. For IP reasons, I am not giving the full structure here. So this is BAFTA, we call it by Vishnu thalexyl phthalic acid amide. So we developed this molecule, and so these are the salient features. If you want to manufacture, it is it can be manufactured easily. The available materials, single step reaction. That is the beauty of our theoretical calculation. We can do the reaction in single step. Again, it is very easy to scale up and to the commercial scale. The thing is that the properties of this solvent is very well matches with the current solvent extraction circuit. So there is no additional infrastructure requirement. Regeneration is easy, stripping done with 0.5 mole HCl. So because we are not adding any thiocyanate, so it becomes a trouble-free process. And again, if you see the design part, so we are actually taking only carbon, hydrogen, nitrogen, oxygen element. So these elements are perfectly incinerable. So again, the spent solvent management is easy, and that's why I am putting this in green color, because it is becoming a green thing now. This is how to do it. So this is DFT optimized geometry. If you see, I have taken only 4 layers: lanthanum, yttrium, europium, and lutetium. And if you see the bond distances from lanthanum onwards, because the lanthanide contraction you are having, until lutetium, the bond distances with the ligand actually they are becoming shorter. The beauty is that in case of yttrium itself, additional water which is not here comes into the picture, and it is because of that hydrated water, the yttrium remains in the aqueous phase, even the lanthanum remains in the aqueous phase, or not only heavy rare earth, they are going to the organic phase. So this we got from DFT things, and later on when we did the experiments, we get the almost similar kind of things. So this is BAFTA. So what we have seen that very low extractability of yttrium in the organic phase. So majority of yttrium is going into the raffinate phase, very easy to separate, and even high extractability of heavy rares in the organic phase. If you really compare this molecule with what is reported for Ca100 and Pc888, in fact it is giving much better result than the Ca100 also.
Dr. Ruhela.
Yeah, only 2 molecules. Yeah, so this is another challenge. So this is NDPR. Lot of things are going on here. That okay, we have some limitations with NDPR. It is not easy to separate. And right now they are having 120 stages. At least worldwide they are having 120 stages for NDPR separation. We took this challenge, and the reason is that if you go to the extractant itself, it will tell the reason. The NDPR, they are very close. F orbitals are almost empty. So you have very weak interactions you have to exploit. But for that exploitation, the Pc888 or these kind of molecules, they are actually not meant for this separation. But because we are not having the molecule, we have used. See, I have shown the electron density map here. So with all these molecules, the electron density is going to the harder direction. Means you want to separate 2 very closely placed metals, and you are using a hard donor thing. It will not happen. So what we have done? This is a molecule which we have designed. If you really compare with the first thing, our electron density is really diffuse. If you see the red bar, in earlier slide it was very very concentrated thing. Now it is diffused, and because of that this diffusivity, we have exploited the subtle difference in f orbital interactions, and because of that interactions which I have shown here, actually we have achieved a separation factor of greater than 2.31. I will tell you where that with the commercial thing it is only 1.2. And with this separation factors, the stage requirements coming drastically to 50 only. This I did in my postdoctoral thing. It is coming at plant scale, so I am not touching now. And I will touch upon a little bit on this the solid polymeric phase resins. So this is all we know. These are commercial ion exchangers. The thing what we have done, we have designed a ligand. This is again again a very particular problem which we are having. So in some of the streams we are having rare metals, but the acidity is like pH 1 or so. So we want to have a resin which can work at these acidities, which can only extract rare element and which can leave the alkaline and transition metals. And with this resin we have got very good results, and it can work to the 2 sub ppm to 2 to 5 gram per liter overall rare chloride it can take, and it can reject even the iron and aluminum kind of thing. So this is a thing which I want to put, that we can have some solvents with better separation factors, even which are not available worldwide. We can make some ionic liquids, especially for rare separations, which will have smaller footprints, small capex and opex, and volume to be treated as low. And at the end of the day, we can have some ligand grafted resins which will having very high selectivity for, especially for rare elements, to take care of lead sources and effluent streams. Thanks.
Thank you very much. Unfortunately, we don't have time for question and answers. Though I believe particularly the last 2 presentations, Dr. Ranjan and Dr. Ruela, possibly would warrant few questions from you. Please carry on that during lunch and after lunch. And we close the session, this particular session. And I thank all of you on my and my co-chair, Professor Sahendra Singh's behalf.
For the excellent presentation that truly highlights India's growing research strength in critical metal technologies. Now I would request Professor Satrughan Soren to felicitate our chair.
First, I would like the chair and co-chair to felicitate the speakers with the mementos.
Dr. T. Srinivas, Dr. Ranjan Singh, and Dr. Ritesh Ruhila. Now I kindly request Professor Satrughan Soren to felicitate our chair and co-chair. I request all the participants request all the participants of the next session to submit their presentation in the dais room.
I would also request the crowd to move for lunch, and we will be starting the next session at 3 p.m., which will be on advances in critical metal sciences and technology.